Well, welcome back. You started up the video notes again, and therefore I know that you're ready to check some IUPAC names as we practice naming alkenes. We've been working hard at identifying the longest carbon chain that contains the multiple bond, be it a double or a triple. It must be in the longest chain, and then to make sure that that double or triple bond gets priority in the numbering system, making sure it receives the lowest number possible. So let's just go to work with letter A. We have a 1, 2, 3, 4, 5 carbon chain. And I can see a substituent group of a 1 carbon methyl coming off of carbon number 3. So we'll let the reader know by naming with location and the prefix meth that there is a methyl group coming off of the longest carbon chain at the position 3, 3-methyl. I also need to let you know that in between carbon 1 and 2 contains a double bond. So you'll see the 1 dash. Remember that any number and letter is separated by a dash. Any number separated by a next number receives a comma. So 1 dash, and then with 5 we get a pent. Whoops, I misspelled. We get pent, and then the double bond, ene. 3-methyl 1-pentene. Good work. Now letter B, you might find it a little helpful to kind of sketch the connectivity. This particular carbon that's involved in the double bond has 2 groups of ethyl coming off of it. So just to kind of see what that structural compound looks like, carbon that contains the double bond has 2 groups of 2 carbon chains attached. Then off of this carbon, we have 1, 2, 3 more carbons in that particular chain. So I just like to sketch out so I can see what I'm trying to name. Now let's number. Here we have carbon 1, 2, 3, 4, 5, 6, 7 in the longest chain. And just to verify ahead, we count 1, 2, 3, 4. Looks like we could have yep, so we're good. The lowest number would be achieved from left to right, and so we keep the numbering as I had practiced first, but I like to double check to make sure that we indeed found the lowest number for the carbon bond. At carbon number 3, there is an ethyl group. That's a 2 carbon chain coming off of carbon 3. The longest carbon chain was 7, and in between carbon 3 and 4 is the location of our double bond. So here we hear the last name heptene, letting us know the double bond position in addition to the substituent group position. So we simply say 3-ethyl, 3-heptene. How about the next one in letter C? Oh, I can see that we have a 2 double bond location. I'm going to number it 1, 2, 3, 4, 5, 6, 7. And I just want to compare that had I numbered left to right. 1, 2, 3, 4, 5, 6, 7. Numbering right to left gives me the first double bond location at position 2 and the next at position 4. Had I numbered left to right, we would get a double bond position between carbon 3 and 4, and then again between carbon 5 and 6. So I choose to go this direction, right to left, because a 2-4 numbering system is a lower numbering system than a 3-5. Okay, so we just had to double check which way gets us the lowest possible number. We can see that we have 7 carbons in the longest carbon chain, and I need to let you know where those double bonds are located. The first is located, this is letter C, by the way. There. The first is located between carbon 2 and 3, and the next is between carbon 4 and 5. The chain itself is 7 carbons long, so see how we do hepta, see the little A in there, hepta, diene, and we've properly named letter C. No substituent branches, we were just naming both double bonds. Now let's take a peek at the last structure, letter D. Letter D contains a double bond and a substituent group. The priority has to be to place the double bond between carbon 1 and 2. We have to have carbon 1 and 2, the location of the double bond. Then I'll keep numbering around the system to see the substituent branch, the 2-carbon chain of ethyl coming off of carbon number 3. Now, if I redraw this just to show what not to do, I would not want to number 1, 2, 3, 4, 5 because 5 is a higher substituent number than the number 3 that we numbered up above. So we have to number going clockwise and making sure that between carbon 1 and 2 is indeed the double bond. So I'll let you know at carbon 3, there is a substituent group of ethyl. That's a 2-carbon chain. Notice in the cyclo group, I do not let you know that at carbon 1 there's a double bond because you already know the double bond is at carbon 1 to 2. So we'll simply go straight to saying cyclo and then the prefix pent for 5 and then ene to let you know there's a double bond. 3-ethyl cyclopentene. How'd you do? Oh, I know you're doing well. That's what practice does. It makes you better and better each time. Let's try some alkynes. Alkynes, of course, mean they have a triple bond. So really the only difference now, instead of ene, we end them with yne. Here I notice that this particular carbon has a branch of 2 carbons coming off of it. So just to keep that in mind, it has 2 methyl groups coming off. So that's this carbon. It's next door to a carbon that's involved in a triple bond. All right, so that's here. And then we have 1, 2, 3, 4, 5 more carbons. 1, 2, 3, 4, 5. So just kind of sketching this long chain. I can see that numbering from right to left will get us the lowest number for the triple bond. So I'll start out by doing that. And how many carbons total do we see in that particular structure? I'm going to just double check. 1, 2, 3, 4, 5, 6, 7, 8, 9. And the other methyl is a chain. So that looks right. We have 9 carbons in the lowest or in the longest carbon chain. And at carbon 2, there is a methyl group. So I'm going to locate the substituent branch as 2-methyl. I will let you know that between carbon 3 and 4 is a triple bond by using the prefix known for 9 carbon chains and ending it with the YNE suffix to let you know that the multiple bond is a triple. So that's simply called 2-methyl 3-no-9. No-9 is its pronunciation. These are fun. Here we have 1, 2, 3, 4, 5, 6, go up, 7, 8. That's the longest chain in that particular structure. I'm going to double check my numbering to be sure I've arrived at the lowest number possible for the triple bond. Let me just double check. It's always wise to double check. 1, 2, 3, 4, 5, 6, 7, 8. Numbering right to left places the double bond at position 5. Numbering left to right places that triple bond at position 3. So this is the correct ordering. Alrighty. So what about substituents? We have 2 methyl groups. Both of them are coming off of carbon 6. So let's let you know 6, 6. Remember, every substituent needs its own number. Even if it's the same number, you have to repeat it. 6, 6, then a dash. We're going to separate a number to letters. I'll let you know that both groups are the same by using a di prefix. 6, 6, dimethyl. Then I'll let you know that there is a triple bond between carbon 3 and 4 by putting a locant there of a number 3. The prefix for the number 8 is oct, and the triple bond receives the suffix of -ine. 6, 6, dimethyl 3-octyne. Oh, you're doing good. Super proud of you. I recommend pausing the video, work these out, and then come back to me when ready to check. Don't cheat yourself of the practice. Your learning deepens when you practice first and then turn the video back on. Okay, welcome back. Let's go to work. Let's find the longest carbon chain in our very first structure. So let's see. I have a 1, 2, 3, 4, 5, 6 carbon chain. I get the same numbering system had I gone from the bottom around. 1, 2, 3, 4, 5. That works the same as if I go straight across. How about if I go right to left? 1, 2, 3, 4, 5, 6. Well, this looks like multiple options. This looks like an opportunity to really have no wrong answer, because either way, I'm finding that the double bond is between carbon 3 and 4, and I'm finding that carbon 3 has an ethyl substituent branch. So since all the numbering choices get me the same, I'll just do straight across. At carbon number 3, there's a 2-carbon substituent. That 2-carbon gets an abbreviation of ethyl. Then I'll let you know at carbon 3, there's a double bond in a 6-carbon chain. Hex represents the prefix 6. 3-ethyl, 3-hexene. How'd you do? Oh, these aren't so bad. Carbon 1, 2 will give the location of the double bond, the lowest number, and I'll just keep numbering as we go across. Looks like we have 8 in the longest carbon chain, and we have some methyl groups coming off at carbon 4 and at carbon 5. So let's name the substituents. 4, 5. We have the same substituent, so we'll give a prefix of di. So that's 4, 5 dimethyl, and then letting you know that the double bond is located between carbon 1 and 2 of an 8-carbon chain gives you 4, 5 dimethyl 1-octene. Beautiful. Okay, how about the last one? Remember that the longest carbon chain must contain the multiple bond. So I'm going to choose to start numbering down here and see what I find. I can find a 6-carbon chain. It didn't matter if I started over here to the left or over here where I did to the right. And even though I could find a carbon chain that's long, I need to make sure that I have the double bond. All right, so that looks like a 6-carbon ring. And I have a methyl group coming off of 3 and 2. So I'll let you know that with a 2, 3 dimethyl. And this carbon chain was a hex, being that it was 6 carbons long. And the ENE lets you know these were all double bonds. So from line structures or condensed structures, we're still able to practice our ene-ine nomenclature. Now, I also wanted to include some practices where you had to read the names and then come up with the structures. So there's 2 of them here. A letter A says 5,5-dimethyl-3-heptine. So I recommend, let's go to this very root word. Before I worry about branches off of the main chain, let's get that long carbon chain drawn. The prefix hept means 7. Ine means a triple bond. And the location of the triple bond means it's between carbon 3 and 4. So I'm going to draw 7 carbons in a row. And then on position 3 to 4, I'm going to make sure you see that there's a triple bond there. So that's the backbone, 3-heptine. Now I can go and look at what branches are coming off of the main carbon chain. It says at carbon 5, I have a methyl and another methyl, a dimethyl coming off of the same carbon. So that would represent kind of the connectivity of this structure. Now, if I were to draw this into a line structure, remember that a triple bond is a very flat area, that this is 180 degrees. So remember the trick? I want you to draw a long line and then place a triple bond kind of in the center of it. Whoops. That was my fingers. There we go. Now in this picture, this carbon involved in the triple bond here is between carbon 3 and carbon 4. Next door, coming straight out of it, is carbon 2 and carbon 5. See how that works? So that all that long linear area represents the molecular geometry between carbon 2, 3, 4, and 5. And then coming off of carbon 2, we have a branch. Now I can go up or down. It doesn't matter. It's going to branch up. There's carbon 1. And then coming out of carbon 5 to carbon 6 and 7, we have to zigzag. Again, it doesn't matter if I go up or down. I'll just go up and then down. So here's carbon 6 and 7. And remember that carbon 5 had 2 methyl groups. Since I had carbon 6 coming up and I don't want to squeeze in, I want to ease crowding, I'm going to place the 2 methyl groups coming down off of carbon 5. So there's my linear structure, the skeletal structure, bond line structure of the 5,5-dimethyl-3-heptine. Ooh, cool. Let's try another one. These are fun. 1,3-dimethyl cyclohexene. Again, go to the backbone and begin there. Cyclohexene. Well, the hex tells me 6 carbons, and they're going to be in a cyclic structure. So there's my cyclohexene. Wherever I draw the double bond, it doesn't matter where, I just have to pick a line. I now know that the double bond is between carbon 1 and 2 by definition. So that tells me I need to place a dimethyl. 1 methyl coming off of carbon 1 and the next coming off at carbon 3. Now remember, your structure can look so many different ways. If I had chosen to put my double bond here, awesome. I now know it's between carbon 1 and 2, so I would have 1,3-dimethyl cyclohexene. I could spin it a different way. All of these are exactly the same. Let's put a double bond there. I'll number it 1, 2. So the double bond, dimethylhexene at position 1, 3. I'm emphasizing that those are all the same structure. I'm just twisting the same molecule in space, twisting it around to look at it from different angles. Let's keep practicing. Again, this is critical. This is just a fundamental skill that will carry you forward throughout the rest of the semester. So pause me, put the video on pause, try these structures out, and then come back to see if our answers are common. Letter A, 4-methyl-1-hexene. So a hexene, that tells me that I have 6 carbons in a chain with a double bond between carbon 1 and 2. 1, 2, 3, 4, 5, 6 carbons. That's the same as saying 6 carbons in a row. I'm just letting you know their molecular geometry is a up, down, zigzag line. And between carbon 1 and 2 is a double bond. Off of carbon, sorry, my hand hit the screen. Off of carbon 4 is a methyl group. So here is a methyl group. So carbon 1, 2, 3, 4 is your methyl. 4-methyl-1-hexene. Now again, I can draw these as just kind of an idea of connectivity and then go to the bond line structure based on the name. Let's look at 5. Again, bring your eyes to the very last part of it, 2-heptene. That tells me hept means 7. So I'm going to draw 7 carbons in a zigzag line. 1, 2, 3, 4, 5, 6, 7. There's the backbone. Between carbon 2 and 3 is a double bond. E-N-E, double bond. Between carbon 1, 2, and 3. So there's the double bond. At carbon number 2, we have a methyl group. And at carbon number 5, 1, 2, 3, 4, that's here. Carbon 5, we have an ethyl group. That's a 2-carbon chain. So there is our structure for letter B. Numbering it just to verify. 1, 2, yep, 2 has a methyl group. Between 2 and 3 is a double bond. And off of carbon 5 is an ethyl group. Let's try letter C. 2,5-dimethyl-3-hexyne. There is a 3-carbon chain. There's a 6-carbon chain, and at carbon 3 to 4 is a triple bond. So remember how I like to do this? Let's get our feet wet. There's 1, 2, 3, 4, 5, 6. Between carbon 3 and 4 is a triple bond. Off of carbon number 2 is a methyl. 1, 2, 3, 4, 5 is another methyl. So remember the trick, draw a straight line, and then in between there, just kind of put a triple bond representing the location of the triple bond between carbon 3 and 4. Next door, of course, is carbon 2 and 5, but they come out in a linear fashion. That is a straight line in that molecule. We're at carbon 5. Notice 5 has 2 methyl groups coming off of it. Carbon 2 has 2 methyl groups coming off of it. So again, I'm just going to choose to go up and down, up and down, and those are going to represent carbon 1, 2, 3, 4, 5, 6. And you can see at position 2 and 5, there are methyl groups. And that's the look of that particular molecule drawn to the correct geometry. All right, letter D. 1-propyl cyclobutene. I like to draw the backbone first before I worry about substituents. Cyclobutene tells me that's a square, 4 carbons in a cyclic structure. Ene tells me double bond, so I can pick any of the sides and let's draw a double bond. And by definition, I now know the position of the double bond is always between carbon 1 and 2. Coming off of the first carbon, we have a 1, 2, 3 carbon chain. That's the propyl prefix there. That's 1-propyl cyclobutane. In letter D, we just drew 1-propyl cyclobutene. Let's take a peek at E. 1,3-cyclohexadiene. Oh, we've got 2 double bonds. Those double bonds are going to be located between carbon 1 and 2 and between carbon 3 and 4. So start by drawing a cyclo, and again, hex means 6. So I'll place 6 carbons in a cyclic structure. That's a 6-membered ring. When I draw my first double bond, I've just given definition to all of the numbers in the cyclic structure. The double bond must be located between carbon 1 and 2. The next one has to be located between 3 and 4. And there it is. That's 1,3-cyclohexadiene. And letter F, our last one on this series. 4-ethyl-1-decyne. That's 10 carbons in a row. So let's look at this example where I were to draw the triple bond, which this has INE, except remember I told you that this would represent the 2 carbons in the triple bond, assuming there's 1 carbon to the left of the first, but there's not here, is there? The first carbon is the one in the triple bond, so that means I have to start with the triple bond in the structure. Now remember that H would be coming off straight out, but I don't draw H's in these line structures. So carbon 1 to 2 is the triple bond. Carbon 3 still comes straight out. We still have to follow that rule that the next carbon comes out. But then I start zigzagging for the rest because those are all going to be single bonds. Now there's a total of 10 carbons Between carbon 1 and 2 is the triple, and I'm at carbon 3, so I'll just start zigzagging. 4, 5, 6, 7, 8, 9, 10. Let me check my work. 4, 5, 6, 7, 8, 9, 10. We did it. Now, how about the substituent? At carbon 4, there's an ethyl group. So I want to give it room. I'm going to put it up and then out. That's a 2-carbon chain, thus ethyl, coming out at carbon 4 in a 10-carbon chain that has a triple bond between carbons 1 and 2. All right. Woo, we're doing it. In our next section, I want to talk about another type of isomer called a stereoisomer, specifically a cis-trans configuration. Now let me review from our previous vocabulary word. This is a word we've said already called a constitutional isomer. Remember that these are molecules that share the same molecular formula but have a different connectivity. Constitutional isomers have unique names. So if I'm naming two compounds and come up with the same name, they're the same compound. If I'm naming compounds and they have the same molecular formula but a unique name, they are constitutional isomers. So for example, each of these compounds in this example contain 4 carbons. They contain 4 carbons and 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. They have the same molecular formula. Therefore, by definition, they're called constitutional isomers. But notice that the location of the double bond or the number of carbons in the longest carbon chain are different, right? So they're connecting their atoms in a different order. That's what we call a constitutional isomer. They are different molecules. They have different reactivity. They have different physical properties. The only thing they have in common is the number and kind of each atom in their formula. So let's talk about a different type of isomer known as a stereoisomer. A new class has been heard from, stereoisomer. Keep in mind that when we have a multiple bond, such as a double or a triple, that bond has restricted rotation. They cannot move. Single bonds have complete freedom to rotate. And that's why we're saying there's so many correct ways to connect structures. If I want to connect 5 carbons in a row, 1, 2, 3, 4, 5, that's okay. I could go 1, 2, 3, 4, 5, that's okay. Because as long as they're connected in the same order, you're giving the same molecule, because single bonds have freedom to move. They rotate in space. But double and triples cannot move. They are restricted rotation. They're rigid. They cannot twist and bend in space. So therefore, here's a molecule called 2-butene. Notice I have 4 carbons in a row, and the location of the double bond is between carbon 2 and 3. We actually have 2 different spatial arrangements for this 2-butene. If I connect carbon 2 and 3 in a double bond, remember that this is fixed rotation, that that's a rigid, very restricted group. That double bond cannot rotate in space. Carbon 1 and 2 have a choice of connect. Remember that we have trigonal planar. I'm going to just emphasize the molecular geometry here is trigonal planar. So that means there's a 120-degree bond angle coming out of that carbon. Same here. This is trigonal planar on the opposite side. And therefore, we have a 120-degree bond angle between the methyl and the hydrogen. All right, so an equilateral triangle. but they do come out and are fixed in their position. If we place both methyl groups on top of the plane of the double bond, they're on the same side of the double bond. We call that the cis, meaning same side. If the two methyl groups at carbon 1 and at carbon 4 are on opposite sides of the plane of the double bond, opposite sides represents the trans isomer. Now remember, when I say cis and trans, this bond, remember, if we think of it as being single, we might want to think that we're just twisting the molecule. I cannot twist, cannot do this to turn a cis into a trans. It's impossible to just twist and get one to convert to the other because it's a rigid bond. It does not rotate. So to convert a cis to a trans, I have to break a bond. I have to break this bond, and relocate those groups. And so that does not happen, right? You just can't twist to convert. It means that they are actually located in a different position. And yet the connectivity of the atoms is in the same order, right? I still have the longest carbon chain as 4, but because they've arranged them in a different kind of a molecular geometry, different spatial arrangement, we call those stereoisomers. Think of the term stereo as a spatial arrangement. How are they connected in space? If it's on the same side of the double bond, we call that cis. If it's on the opposite side of the double bond, we call it trans. Stereoisomers are indeed a new class of isomer based on the location of the groups coming out of the double bond. Here is the same molecule just drawn for us in a ball and stick fashion. Notice that the cis configuration places carbon 1 and 4 on the same side of the double bond, and the trans isomer places the carbon 1 and 4 on the opposite side of the plane of the double bond. You cannot twist this. That bond right here cannot just simply twist to convert from one configuration to the other. They are held in a fixed position, and therefore they are considered stereoisomers. Cis is same, trans is opposite. Whenever the two groups on each end of the carbon chain, the double to double bond carbon, are different from each other, we have two isomers that are possible. Notice that at carbon in the double bond has two groups coming off of it. A and B must be different. C and D must be different from one another. A cannot equal B, right? They cannot be the same. And C cannot equal D. In order to have cis-trans isomers, you have to have different things coming off of the carbons in the double bonds. Now let's kind of model what that means. For example, if we have two groups on one end of the double bond that are identical, notice here that carbon involved in the double bond has two identical groups. Let's call them both hydrogens. It's impossible to have a cis-trans isomer because if I switch these two hydrogens, it's exactly the same molecule, right? So there's no interchangement of that particular compound. That H's have to be different. I have to have maybe a carbon and a hydrogen or a carbon and a chlorine, but they cannot be the same. They must be different. Notice on this side, H is very different from an ethyl group, but over here, H is the same as this H, so therefore no stereoisomers possible. We have to have, on the same carbon involved in the double bond, you have to have different groups attached. Let's practice. Let's draw the cis-trans isomers of 3-hexene. So let's kind of just start by sketching what that is going to look like. I have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And between carbon 3 and 4 is a double bond. All right, so I'm just kind of getting my feet wet of what I'm going to sketch here. I know between carbon 3 and 4 is a double bond, so why don't I just make those kind of my starting point? That means carbon 3, because it's trigonal planar, has 2 bonds coming out of it at 120 degrees. Carbon 4 has 2 bonds coming out of it at 120 degrees. That's what trigonal planar means in molecular geometry. Carbon that's leading to just 3 other atoms has a trigonal planar geometry, bond angle of 120. So just reminding us that that's 120 degrees either side. So on one side, I have an ethyl group coming out. On the other side, it's an identical ethyl. We have 2 carbons left. So if it's a cis configuration, that tells me that those 2 carbons and the ethyls there are going to be on the same side. So I would have 2 carbons, and to complete the octet there, we would have 2 hydrogens. This is the cis configuration. Notice that the plane of the double bond has the entire backbone of the carbon chain on the same side of the double bond. Same meaning cis. How about here? If I redraw carbon 3 and 4, knowing that coming out of any double bond are 2 more bonds at 120 degree bond angle, but I want to make them trans. Opposite means trans. So I'm going to place carbon on top, carbon 1 and 2, and on the bottom of the plane, I'll put carbon 5 and 6, meaning that the H's are on opposite sides as well. So when the carbon chain starts on top of the plane and ends below the plane, or vice versa, we have the trans configuration. Now in a line structure, what would that look like? If I was drawing trans, 1, 2, 3, 4, 5, 6, between carbon 3 and 4, there's a double bond. Notice that the double bond has the next carbon chain going down and the next carbon chain going up from the double bond. The double bond, so I draw the plane, one is coming down, the other is coming up. So that's the trans configuration. In this particular section, cis, if this is our double bond, carbon 4, 5, carbon 4, 5 are coming up on the same side. 1, 2, 3, 4, 5, 6. Between carbon 3 and 4 is a double bond, but notice that here's the plane of the double bond, so they're coming up together. Remember, those are single bonds, so they can twist. You know, that's the same structure, they're just coming together. But the emphasis is that from the plane of the double bond, you see them both on the same side of the plane. That's a cis configuration. This is the trans configuration. You can see just based on crowding of the molecules, the trans is the preferred molecular geometry because it gives more space for the atoms to spread out. This is a very crowded condition, which means it's an unstable configuration, where this is very much spread out over here, lots of room for all the atoms, so it's preferred, it is more stable. Everyone likes to have room to not crowd next to another atom. Let's try some more practices. Here's an A, B, and C. If you'd like to pause, please do so and give yourself some idea of just practicing. Think through first, then come back to me when ready. Okay, now here it says condensed structure. So that's not the line structure, but I tend to do both just to keep practicing. I have an ene, so I know I'm just going to start by kind of figuring out connectivity. So I have 1, 2, 3, 4, 5, 6, 7, 8. That is 8 carbons in a row. At 1, 2, let me just number so keep track of it. Here I have 8 carbons, and between carbon 2 and 3 is the double bond. Alrighty, so that's good there. And then we want to figure out the configuration to be cis. So start by drawing your double bond, and then keep in mind that they both have to be on the same side. So carbon number 1 has to come down. Carbon number 3 has to come down, and then carry on the chain from there. Now, I could have put both up. I can place both down. It does not matter. I just wanted to be sure that we see they're the same side. 1, 2, 3, 4 so far. So 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So I'm giving you a little idea also of molecular geometry. I could draw those in a straight chain from carbon 4 through 8. I'm just letting you know it starts again to zigzag there. Those are all single bonds. How about trans 3-heptene? Trans 3-heptene. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And between carbon 3 and 4 is the double bond. So start by drawing the double bond, and you know it's between carbon 3 and 4. Now I can choose, remember that there's 2 bonds coming off, right? This is a hydrogen here. This is a hydrogen here. Those are the 4 bonds required. So I can see that I have a hydrogen coming off, and then another bond going down. I have another bond coming up, another bond coming down. That's the trigonal planar molecular geometry of a double bond. To make them trans, I'm going to put a hydrogen on opposite sides to help me remember that the carbons have to be on opposite sides. So here's carbon 2 and 1. 1, 2, 3, 4, and I need a total of 7. So 5, 6, 7. There is the trans configuration of 3-heptene, opposite sides for trans. And then, just to kind of think that through, these would be, up, down between 5 and 7. It's up, down, any single bond. Trans 4-methyl-2-pentene. Start at the backbone, and let's figure out what the connectivity is. 1, 2, 3, 4, 5. At carbon 2 is a double bond of a 5-carbon chain. And at carbon 4, there's a methyl group. All right, so that's our view so far. Start by drawing carbon 2 and 3 with their double bond. And then remember, those double bonds means that carbon has 2 more bonds coming out at 120 degrees. We're asked for trans. So just let yourself know trans means that they're opposite sides for the carbons. You could think of that as opposite sides for the hydrogens. Cis means the same. Trans means opposite. So there's carbon 2 and 3. Coming off of carbon 2, there's 1 more carbon. Coming off of carbon 3 is a next carbon, carbon 4, and it will have 2 methyl groups coming off of it. That represents the trans configuration of 4-methyl-2-pentene. In this picture, we're being asked to just judge each one of these double bonds and recognize if it's cis or trans. So let's do this particular bond first, for no other reason than it's the one I saw first. And look at the plane of the double bond. The hydrogens are up above in the same plane, and the carbon chains are below in the same plane. Since these are both in the same plane, both are up for hydrogens, both carbons are down. This means that configuration is cis, the same. Now let's consider the next double bond. Looking at C double bond C in this position. Let me just clean this picture up so we can view the second bond cleanly. Here I notice that the carbon is pointing up and this carbon is pointing down. Or this hydrogen is up, this hydrogen is down. They are on opposite sides of the plane of the double bond. So therefore, we can recognize that's the trans configuration. What I highlighted, let's say in green, is cis, and what I highlighted in purple is the trans configuration. Stereoisomers are isomers that differ only in the 3D arrangement of atoms. Constitutional isomers differ in the way the atoms are bonded to each other. We've been practicing both. We started with considering constitutional isomers. Those have the same molecular formula, but connect their atoms in a different order. Remember, constitutional isomers will have unique names. 1-butene is a different name than cis-2-butene. 1-butene locates the double bond between carbon 1 and 2. But remember, 1-butene cannot have cis-trans configuration because that first carbon has same attachments, hydrogen and hydrogen. Remember, on the same carbon here, this first carbon would need different attachments in order to have a configuration of cis or trans. And that's the occurrence we have with these stereoisomers, cis-2-butene and trans-2-butene. They connect their atoms in the same order, right? Single, then double, then single bond in that 4-carbon chain. They're attached in the same order, but they have a 3-dimensional stereoisomer. If the attachments are on the same side of the plane of the double bond, it is cis. If they attach those groups on opposite sides, up and the other down from the plane of the double bond, we called it trans. Let's think that through with this example. Label each pair of compounds as stereoisomers or constitutional isomers. Let's compare A with B, and then we'll look at A with C. Well, let's first figure out if we have the same or different. So I have the longest carbon chain that contains the double bond. 1, 2, 3, 4, 5. At carbon 1 is an OH group. So between carbon 2 and 3 is a double bond. And at carbon number 1, we see that functional group of an alcohol. Just kind of making notes what makes that compound kind of special. Let's go to work over here. At letter B, I'm going to number 1, 2, 3, 4, 5. The alcohol, the OH, is attached to 2 single bonded carbons before we get to the double bond. As a matter of fact, I could number this to get the double bond at a lower number. Between 2 and 3 is the double bond, but the alcohol attached to 1 carbon, then the double bond. Here the alcohol is attached to 2 carbons, then the double bond. They are attached in a different order. So A with B represents constitutional isomers because of different conductivity. Let's compare A with C. I already looked at A. Let's examine C. I have 1, 2, 3, 4, 5 carbons. That looks good. The alcohol is attached to just 1 carbon, then straight to the double bond. I like that. You know, as we examine this, A and C are exactly the same order of attachment, except we are switching from cis and trans. In letter C, both carbon chains are on the top. That's a cis conformation of the same connectivity of atoms. In letter A, this is the trans conformation on the plane of the double bond. One carbon group is up, the other carbon group is down, but it's the same connectivity. So therefore, these are considered stereoisomers. Great. We're doing great. Label these as constitutional or stereoisomers. Are they the same, in terms of molecular formula? And then from there, are they arranged in different connectivity, or are they arranged spatially different but same connectivity? So just think about that. What I'm saying is different connections stereoisomers have same connection, but you'll see a cis-trans conformation. And if neither of those meet the criteria, they might be different molecules altogether. That doesn't have to be, but it looks like in this example, we're telling you that these are pairs of alkenes that are isomers. We want to decide if they're constitutional isomers or stereoisomers. Alrighty. So what do you think about letter A? Right off the bat, I can recognize that the location of the double bond is different. That the double bond is located between carbon 2 and 3 in the first structure, but here it's located between carbon 1 and 2 in the next structure. Therefore, that's different connectivity. So right away, just based on that location, I know that these are constitutional isomers, different connectivity. Now let's go to work here. Letter B. I have 1, 2, 3, 4, 5 carbons. Looks like the plane of the double bond puts these all on the same side. That is a cis conformation. Here again, I have same number of carbons. There's 5 carbons in the longest carbon chain, but one of them places them on top of the plane of the double bond, and the other places them below the plane of the double bond. Therefore, that's a trans configuration, making these stereoisomers. Now look at this one in letter C. I notice here, this one here, this carbon that's involved in the double bond leads to an ethyl group, and coming down here leads to a methyl group. And then these are the same. These are both hydrogens. That's different over here, isn't it? The carbon in the first double bond has an ethyl, but the methyl has been replaced by a hydrogen. The second carbon here in the double bond has a methyl and a hydrogen. These are connected in a different order. My writing is not working well on the screen at the moment. It's connected differently. So let's report that as a constitutional isomer. Now we've got it. Because both carbons in the double bond lead to different attachments, they are not the same compound. They would have unique names. Are these cis or trans? Now I'm going to look at some cyclic structures and decide if these are cis or trans configuration. So let's find that double bond, right? And that's going to represent the plane. Just kind of draw a line, extend that double bond, and that's the plane. Notice that the carbons are coming to the same side. They're both on the right side of the line I just drew. So that particular conformation would be a cis configuration because they come off of the double bond in the same direction. They're both pointing on the same side of the plane. So letter A is a cis conformation. How about B? B gives us two different ones to examine. Let's do this first bond here. Now again, what I like to do is just take the line of the double bond and kind of extend it, and that becomes the plane of the double bond. Look at the carbon group goes in that upward direction on one side, and it goes on a downward direction on the other side. If one's up and one's down, that one happens to be trans. Let's draw a line from the double bond just to extend and find the plane of the double bond. Both carbons are heading out in the same direction. That's to the left of the line. The same direction would be a cis conformation. So letter B gives us an example of a trans on the left side and a cis on the right side of the molecule. One of the applications of a cis-trans isomers occurs in a fatty acid, and it's just kind of a nice wrap-up to put an application process to understanding the value of cis-trans isomers. So generally, we see double bonds in all kinds of naturally occurring molecules. Fatty acids are unique in nature because they prefer the cis conformation, which happens to be the more crowded conformation. We'll also notice that as the number of double bonds in the fatty acid increases, the melting point decreases. The more double bonds, the lower the melting point. So for instance, you hear of things called fatty acids, fats, that have few double bonds or no double bonds. Fats are generally formed from fatty acids with very few double bonds, and they typically be solids at room temperature. The more and more double bonds you place in that structure, you tend to be a liquid at room temperature. Think about a stick of butter, for instance. Butter is a naturally occurring fatty acid that contains very few double bonds, and a stick of butter, of course, is a solid at room temperature. Whereas oils, think of vegetable oil, such as corn oil, olive oil, all kinds of different avocado oil, all these different oils, and they generally have liquids at room temperatures. You pour an oil, you cut a butter, because these oils have lots and lots of double bonds in their side structures. So we can see different physical qualities based on the number of double bonds and based on the configuration, being cis or trans, within structures that do contain double bonds. So fatty acids, and keep in mind, fatty acids is one of our chapters when we get to the biochemistry part of our lessons towards the end of our term together. These fatty acids contain carboxylic acids. Remember, a carboxylic acid contains a carbonyl carbon, and then the OH group as its functional group coming off of the carbonyl carbon. This is known as a carboxylic acid. That's kind of the backbone there, and it contains long carbon chains. So this R group can be anywhere from 12 to 20 carbon atoms long. Naturally occurring animal fats and vegetable oils are formed from fatty acids. The saturated means all single bonds. Saturated fatty acids have all single bonds, therefore no double, and they're very long carbon chains, making them solids at room temperature. And unsaturated fatty acids, meaning they have a double or triple bonds, means unsaturated. In their long carbon chain, we see double bonds, and therefore you'll see those be the liquids at room temperature. So a direct correlation between how we find fatty acids and the state of matter. Here's an example of a fatty acid known as stearic acid. Do you see the long carbon chain leading up to a COOH, the carboxylic acid functional group? Because there are no double bonds, this is called a saturated fatty acid. its melting point of 71. This would be a solid at room temperature being about 25 degrees Celsius. So you'd have to warm it up to cause the butter to melt, if you will. Oleic acid has one double bond, and notice that it's the cis conformation. Naturally occurring elements such as these fatty acids prefer the cis configuration. Notice they're coming out on the same side of the double bond. We have a very low melting point comparatively to the stearic acid, which was saturated. So unsaturated when I see the double bond, and this would be a liquid at room temperature. Room temperature approximately is about 25 degrees Celsius. Now look at, we have two configurations of a cis double bond. Again, increasing the number of double bonds has lowered the melting point. Notice that here is yet another. This is linolenic acid versus linoleic acid. I have three double bonds. Notice they prefer the cis configuration. The more and more double bonds, the lower the melting point. So as the number of double bonds in the fatty acid increases, the melting point decreases. And notice the conformation that nature prefers for fatty acid chains is the cis conformation. These are just some ball and stick models to give you an idea. When we look back at this slide, those long carbon chains, if you wanted to see the visual of what the connectivity of the atoms looks like, look at here, this is the functional group of COOH, C-O-O-H. This is that unsaturated chain of stearic acid, just up, down, a long zigzag of all single bonds. Oleic acid with one cis double bond lowered the melting point. Here is linoleic acid. Do you see the double bonds in the cis configuration? Here's one. Here's the next. There's the cis configuration. And in linolenic acid, we said there were three double bonds, all giving you the cis conformation. In that area there, it's hard to see. But that's a nice application to kind of think about why are we learning cis-trans conformation, and there's an application to a biomolecule of a fatty acid. Which would have the lowest boiling point, looking at the ball and stick model of palmitic acid versus palmate oleic acid? Well, right off the bat, do you notice how this is just a straight chain? Even though I say straight, you know it's zigzag, up, down, but you can clearly see that it's what we refer to as a saturated hydrocarbon. They're all single bonds. That long carbon chain means they're all single bonds. I would predict this is a solid at room temperature with a higher melting point as compared to palmate oleic acid, which I notice has a double bond, meaning it is an unsaturated hydrocarbon chain. Because of the double bond, we can see its cis configuration. See how the carbons are coming out of the plane, both pointing down, making that have a lower melting point. And I would anticipate this being a liquid at room temperature. We've done some really good work. It's time to pause. You are going to now use your book to fill in some notes on section 4. What are some interesting things about alkenes we find in food and medicine? And then also section 5, another focus on health and medicine. Using your book, just detail that portion of your note pack, and then we'll pick up our lesson again with section 6 in the next video.